This is the solution for question number 8 from the 2014 Maths Methods paper. Question 8a, we want to use the Cauchy-Schwarz inequality to find an upper bound for this integral. For part B, we want to prove that this result holds, and for part C, we want to apply the Gram-Schmidt orthogonalization procedure to find an orthogonal basis from this basis. So for part A, we use the Cauchy-Schwarz inequality, which is phi of u with v squared is less than the inner product of u with itself times the inner product of v with itself. So I squared is less than or equal to the integral from 0 to 1 of e to the x dx. So we've squared, so it's the square root of e to the x times the square root of e to the x. So that's the inner product of u with u. And here we do the inner product of v with v. So it's square root of 1 plus x squared times the square root of 1 plus x squared, which gives us 1 plus x squared. So that's how we get rid of the square roots. So it's the inner product of u with itself, where u is e to the x, and the inner product of v with itself, where v is the square root of 1 plus x squared. So then these are just simple integrals. We evaluate these integrals. So I, in order to find an upper bound for I, you need to take the square root, and this is an upper bound for the integral. For part B, we note that the inner product of x minus y with x minus y, using the axioms of an inner product, gives you this expression. The norm of x minus y squared, which is this expression here, is then norm of x squared from here, plus the norm of y squared, and then we have minus twice the inner product of x with y, because the inner product of x with y is the same as the inner product of y with x. So those two are the same. And the Cauchy-Schwarz inequality gives us that the inner product of x with y squared is less than or equal to the inner product of x with itself times the inner product of y with itself. So that leads to these inequalities here. And then if you take the square root of all of this, then that gives us this result here. So that's why we have the modulus, is because you take the square root, and that gives you the result. For part C, we apply the Gram-Schmidt orthogonalization procedure, which is given on the summary sheet for your examination. So V1 is equal to U1, so that's just 1, 0, 1. V2 is equal to this expression. And remember, because we're dealing with three-dimensional vectors here, we take dot products. So if you take the dot product of U2, so here's U2 with V1, which we've got there, then you'll see that we do get, this is the same, that's just U2, but this one is 0. So V2 is in fact U2. And then V3, again, we use this formula given here, and we eventually find out V3 is equal to 0, 3, 0. So you can check, if you have extra time in the examination, check that these three vectors are indeed orthogonal to each other. So the dot product of each of these with each other should be 0, and you should be able to see that that's true. So those are easy marks for the examination. And that completes the solution to question number 8, and that ends the examination paper.